I hope you guys understand that. Today, we're gonna go forward from this. So, first of all, we're gonna discuss something called heat capacity. So, heat capacity is defined as the amount of energy required to change temperature of a substance by 1 Kelvin or 1 degree Celsius. Heat capacity is written as capital C. Q is the symbol for heat, and change delta theta is the symbol of changing temperature. So the units of this is joules per degree per Kelvin or joules per degree Celsius. These are the units. Okay. Now, specific heat capacity. This is the amount of energy per unit mass. So when it's specific, it means you're now including mass, and the rest of the definition is same. Required to change the temperature by 1 degree Celsius or 1 Kelvins, like that. The symbols for this is small c and q over m delta theta because it has mass. This is heat energy, this is mass, and this is change in temperature. So the SI units then for this one would be joules per kg per Kelvin or joules per kg per degree Celsius, like that. Please write this down. I just need some water, so I'll be back. Okay, so now let's go forward. I hope you guys have written this. The next thing we got to know, that's called latent heat of fusion. For latent heat of fusion, we got to know it is the amount of heat energy required to completely change the state of a substance from solid to liquid or vice versa. So this is like the first part. The second part is when you write without any change in temperature. You can also write at constant temperature.
2 मिनट सर ये डेफिनेशन याद करनी होगी
Yes, ये याद करने बेटे. Now,
और सर कितने मार्क्स की होगी ये 2 मार्क्स की
2 marks. Yeah.
ओके सर
So the symbol of this is capital L and F. This is equal to Q. That is the formula. SI units would be just joules. Now I'm going to just want to copy this, reuse it again and again. So you guys can write it down. The next one is the specific heat, latent heat of fusion. For this one, basically the only change in this is the same definition really, but instead of writing the amount of heat energy, you're just gonna add. Oh, that's not good. Sorry. Let me copy this. I need this actually. Instead of writing this, now we will be writing the amount of heat energy per unit mass. So this is the only change, right? Let me just add it with a different color. So anything that is specific, you guys need to understand that that means that it is now we're looking at it with respect to mass. Latent heat of fusion is written as small l and f. It will be equal to energy per unit mass. So heat energy, and this would be mass. These definitions you might have already done it in IGs, so it's the same thing. The SI units now will be joules per kilogram, like that. Please write this down. In this chapter, there's a lot of stuff that you need to basically rote learn, a lot of definitions, and some numericals as well. So it's a kind of a mixed hybrid sort of chapter. Okay, now let's now look at the next one, which is called latent heat of vaporization. In this definition, it's basically the same definition as the first one. The only change is that it's now talking about change in state of a substance from liquid to gas or vice versa. So I've just written with a different color so you guys can see the difference. Okay. Latent heat of vaporization is capital L and V, and it is equal to Q. Again, just that. SI units are just joules, like that. I hope you guys get it. Right. Then comes specific latent heat of vaporization. In this definition, everything is the same except for two things. Let me first move this out of the way. Okay, so I'm just changing the color. So first, energy per unit mass. So you gotta include the mass and also from liquid to gas. That's the main change, right? Latent heat of vaporization is written as small l and v. It is Q over M, same formula, where the specific latent heat of vaporization, this is heat energy, that's the mass. And this is basically the SI units are again joules per kilogram, like that. If you guys have any questions here, please let me know. Right. So now these all definitions have a very important, I'd say, impact on how you perceive the questions. I'll show you that in a bit. Right. Should I go forward now? If you don't mind.
Yes.
Okay. Now, it is not required, but it is something I would recommend. Right? So I'm just writing. This is recommended to you people. Whenever you're looking at certain questions, you should draw heating curves and cooling curves. Now, what exactly these are? Suppose we look at for the melting ice. So here we have temperature in degrees Celsius or Kelvins, doesn't really matter. Joules, temperature, and energy in joules. So heating curve means that you're heating something. When you're heating, obviously it will take some time to reach a new temperature. where it reaches the melting point. So it would reach melting point. And when it reaches melting point, this is where it will basically show a constant value of temperature. Why? Because we know at melting point the temperature doesn't change. Then after the material has completely melted, it would start to increase the temperature again. It will reach a new point where it will start to boil.
Sir,
This will yes.
forgive me for asking, but shouldn't the x-axis have temperature as its value?
It doesn't matter.
All
It
right.
doesn't even matter because energy is provided by you. Okay, all right. And when energy is provided by you, it becomes an independent quantity, and because of that, temperature is changing. So usually, what we do in physics is that we want to keep the dependent value on the y-axis. Is it clear? Fun. So when it reaches boiling point, it will start to boil. Now you see the temperature doesn't change because that's what we've studied just yesterday. And then after boiling, it will continue to rise, and that's it. So in this section, it is melting. In this section, it is boiling. So this is a general heating curve. Now, why is it so important? Because whenever you have a change in temperature happening, which is happening from, let me take another color, which is happening from here till here, you got to use energy equals to mc delta theta. This is the specific heat capacity. When it is melting, it's going from liquid to solid to liquid. Then you use latent heat of fusion times mass. You see, in each section there is a different formula. So you this will tell you how many steps have taken now, and then you can apply the formula just adding all the all each part together to find the total energy. In this section again, because temperature is changing, so it will be mc delta theta. In this section again it is boiling, so it will be latent heat of vaporization times mass. Latent heat of vaporization is different from latent heat of fusion because it is harder to boil something than to melt as it requires greater energy. That's why. Again, where the temperature is changing, mc delta theta. So every section you need to see where the temperature is changing and where melting or boiling is happening and apply the right formula in that section. So by drawing these curves, it basically makes your question a bit more clear. I hope you guys understand this, right? In cooling curves, it is the same thing. Initially, you decrease the temperature of any gas. It would start to condense. Condensation will be done at boiling point, obviously. Then you cool it further, and then there will be a time when it will start to freeze. So that's your melting point or freezing point, whatever you want to say, it's the same thing. And then you can reduce the temperature further. This section tells you about condensation. This section tells you about freezing because within that time, within that section, temperature cannot change. Now, obviously, in this section, because the temperature is changing, so we're going to apply mc delta theta. In this section, because the object is changing state. It's going from gas to liquid. We're going to use latent heat of vaporization times mass. In this section again, change in temperature, so mc delta theta. In this section, it is going from liquid to solid, so latent heat of fusion times mass. And then in the last section, mc delta theta is again because there is a change in temperature. Is it clear, everyone? If you guys have any questions, please let me know.
No question.
Right, you guys please draw this. And then I'm gonna go forward. All right. So looking at the first example of this, and then I'll ask you one question. It says, given specific heat capacity of iridium is 1298 joules per kilogram per Kelvin, and its specific latent heat of fusion is 26 kilojoules per mole, like that. It says determine amount of heat required to change temperature of solid iridium from negative 15 degrees Celsius to 3015 degrees Celsius if 5 kilogram iridium is heated. That's the question. They've also given the melting point of iridium 2466 degrees Celsius, and the atomic mass of iridium as 192. All right, so this is the question. Now, obviously, you have to go from negative 15 to 3015. You should also understand in this question that not only that is the range of temperature, but within that there are multiple changes happening. How do I know that? Because melting point is much lower than the final temperature that we got to reach. It means within this whole thing, melting has also taken place. Right. To have a better understanding of the question, I would want to create on the side of the question, which is not required by the examiner at all, a bit of heating curve. So let's see. So we'll start from negative 15 degrees Celsius. First, it will be heated to something like 2466 degrees Celsius, where it will start to melt because obviously there's a change in state happening here. And once it's melted, then it starts to heat up and it will reach something 3 3015 degrees Celsius. That's our last stop. It means now by drawing this, I have a clear understanding that in the first part of the question, I got to use mc delta theta because there's a change in state happening, change in temperature happening. Then I got to use latent heat of fusion times mass. And then I got to use mc delta theta again to find the total energy required. So the functional equation is that the heat energy total is going to be mc delta theta plus latent heat of fusion times mass plus mc delta theta. So this is the functional equation that I need to find. I need to basically put in the values to get the whole answer. But there is another problem, and that is, if you notice, this question has latent heat of fusion in kilojoules per mole. We got to do something about that because we want it in kg. Now we need a symbol exchange. Now let me tell you how. In 1 mole of iridium, I would say there are 192 grams. How do I know this? Because the atomic mass of iridium is 192, right? Which basically means that actually it's given 20, the latent heat of fusion is 26,000 kilojoules per mole. So we are saying that the latent heat of fusion of iridium is 26,000 joules in 1 mole, which is also 192 grams. Is it clear, everyone? Samir, Amna, Abu Bakr, Khadija.
So to convert it into joules per gram, we divide 26,000 by 192.
No, that's not it. Let me tell you how. Just hold on now.
Understood.
Just wait a second. So we want per kg. Yes, you're right. How many grams are in 1 kg? Can you please tell me?
1,000.
1,000 grams, right? So what are we saying? We're saying 26,000 joules in 192 grams. So how many joules in 1,000 grams we're going to cross multiply? Is it clear? So it's going to be 192x equals to 1,000 times 26,000. Now you do this. You don't directly divide it, Afan. Is it clear?
Understood, sir. Sorry.
Because we need per kg, right? So the latent heat of fusion in 1 kg is going to be 1.4 times 10 raised to 5 joules per kilogram, like that.
सर
Everybody
मतलब
understand?
अभी जो आप उसको बता रहे थे वो ये था कि हम उसको सिंपल मल्टीप्लाई बाय 10⁻³ नहीं कर सकते.
नहीं, you cannot.
ओके सर.
So हमें ये पता होना चाहिए कि 1 मोल का जो मास है that is this much, ठीक है? और इतनी एनर्जी 26,000 एनर्जी है, किलो जूल्स है 1 मोल के अंदर, which is actually equal to 192 grams. So 1 kg which is 1,000 ग्राम कितनी एनर्जी होगी क्रॉस मल्टीप्लाई करेंगे. You get it? ठीक है? Like that. Yeah. So you get this answer. Now we are ready to put in the values because this question came out for 5 marks. And I don't think so it's reasonable to lose 5 marks. And if you don't know how to convert from mole to kilograms. So please make sure that you completely understand this. If you do not, still let me know, okay? All right. Now, the mass of iridium was supposed to be 5 kg. So 5. Heat capacity of iridium, I think it was given as 1298. And the change in temperature in the first section was 2466 minus 15. Then latent heat of fusion, we just found out 1.4 times 10 raised to 5 times 5 kg plus 5 kg times heat capacity, which is 1298, multiplied by change in temperature, which is this one, which is from 3015 minus 2466. Again, I'm saying I could do this because I can see everything right here. Otherwise, I would have just forgotten about either this or this. So please make good use of this. This is something that is so valuable. Then the answer final would be 2.0 times 10 raised to 7 joules. Is it clear, everyone? Have a look at this and see if you guys can do this. And let me know if there's a confusion or anything else.
No issue from my side.
Good. Now, the next thing I'm going to do is I'm going to give you people a question that we're going to do in next 8 minutes.
Sir, in the first part of MC del theta,
Mhm.
so the temperature change that we take is from 2466 and then from minus 15.
Yes. So, temperature change is like final temperature minus initial temperature. So, you see,
Hmm, okay.
this is final temperature minus initial temperature. Because it is negative, so obviously you will add the other 15 degrees because it's not starting from a positive number, right? So you just write it.
Okay.
Get it? Should I go forward
Yes,
now?
sir. Yes.
Now let's do a question that I want you guys to solve. And let's see if you guys can do this on your own. It says 200 grams of coffee at initial temperature of 80 degrees Celsius and two ice cubes of 20 grams each are dropped into coffee. Okay. Without any heat exchange from the surroundings, thermal equilibrium temperature is reached. They've given you some of the things as well. So for coffee, they've given you a data. The heat capacity is 4.18 joules per gram per degree Celsius. Initial temperature is given as 80. You guys know this. And the mass is 200 grams. For ice, they have given you latent heat of fusion as 334 joules per gram. They've given you initial temperature of ice as negative 15 degrees Celsius. And they have also given the heat capacity as 4200 joules per kilogram per Kelvin. Also, latent heat of vaporization is 2230 joules per gram. Now, they say determine the equilibrium temperature. And what does that mean? That means when you have added 2 cubes of ice into the coffee, obviously coffee is at 80, ice is at negative 15. So they will basically, coffee will be cooled, ice will be melted, and they will reach a certain amount of temperature together. We need to find that temperature. Is it clear? Think about it. And there's no exchange from the surroundings, which means whatever heat is exchanged, it is basically gone from either ice to coffee or coffee to ice. There's no other third party in this. So think
Yeah, so
about
I have
it.
one question.
Yeah,
Judging from IGCSE experience, we can say that the heat energy absorbed by the ice causes is equal to the heat loss by the coffee, right?
that is correct, 100%.
So the coffee will have a temperature decrease and ice a temperature increase.
Yes,
So if
that,
if we follow that logic, the thermal equilibrium temperature will be somewhere between minus 15 and 80 degrees centigrade, right?
that is correct.
Then how can we use a latent heat of vaporization of ice if ice will boil at 100 degrees centigrade?
That's true. So then don't use it. It's a dummy value.
All right.
Good. ठीक है
Got the answer, sir. Yeah, sir, you're muted.
सर अभी आप कुछ बोल रहे हैं क्योंकि म्यूट हैं अभी आप.
Oh no, that's not fair. I'm sorry. I thought I was not mute. I was saying we have to basically build. You see, ice started from negative 15 and it starts to melt at zero. So that's when you have to use LF into M. And then you go to MC delta theta on top, right? Like that. And then the coffee will cool. Now you guys need to understand ice has three different changes, but coffee has just one change, which is MC delta theta. So what I'm saying is without any other exchange, the heat that is gained by ice cubes has to be the heat lost by coffee. You guys agree?
Yes.
So I'm just writing everything like from 40 to 4.2. I've just changed this. Like you divide by 1000, it will change from kg to gram. And then the change in temperature was 0 minus 15, final minus initial. Okay, enough is plus latent heat of fusion is given, which is 334 times 40. The two ice cubes, that's why. Plus, then we got uh, mass, which is 40. Heat capacity is the same, 4.2. And then the change in temperature is where it goes to theta f minus 0. That's the change, right? So this is what is happening to Chalo, that's bad. This is what is happening to ice. Now, for coffee, the mass of the coffee was 200 grams times the heat capacity of 4.18, and the temperature went from, basically, we gotta do this, 80 minus theta f. Now you might be surprised, why am I writing initial temperature first and final? Because temperature is a scalar quantity. So in a scalar quantity, you take larger minus smaller. You don't do final minus initial. Is it clear, everyone? Like that. Now let's solve this, right? So solving this up, the first part is, it's gonna be something like 15880 plus 168 theta f equals to 66880 minus 8360 theta f. You can actually see. Just take theta f on that side, this side. So it's going to be 104 theta f equals to 51,000. So you divide that. The final equilibrium temperature is going to be 50.8 degrees Celsius. Is it clear?
Yes, sir.
So what I'm saying is that you guys need to, this, like, you could have also drawn this separately. Like for ice, you could have done like this, and for coffee, you could have done like this. It would give you the same result, but then you have to draw two. But that's fine. As long as you basically use this to get the final equation, it's worth your time, because questions like these will be 5 marks and you don't want to lose any mark here. Is it clear?
Yes, sir.
Samir, Ryan, Khatija, Javeria, Dark Legend, and Abu Bakr.
Yes, sir.
यस सर मैं बस 2 मिनट इसको एक दफ़ा दोबारा से देख लूँगा.
Yes, yes, sure, sure. Make sure that if you got the answer the first time wrong, you do it again, okay? It will help build your concepts.
यस सर समझ
Sir,
आ
we
गई.
leave.
Okay, pretty good, huh? All right then. So we're done here, and in the next class, inshallah, we will continue with this.